In this video, we're going to be looking at logarithmic functions. We're going to do two parts to the video. First part will be review of logarithms to make sure that we're comfortable with that concept, and then we'll jump into derivatives of logarithmic functions after we've done the review. So let's start with what a logarithm is. Let's say someone asks us to calculate log base 2 of 1. Okay, well, what we're calculating here is an exponent. It's the exponent that goes on 2 to make 1. So you can ask yourself, 2 to the what equals 1? So for example, if you wanted, let's say this one here, log base 2 of 8, we'd say 2 to the what makes 8? Well, it's 3. So log base 2 of 2 is equal to 1. Let's say log base 2 of 1/2, we'd say 2 to the what gives us 1/2. Well, the exponent would have to be -1. So log base 2 of 1/2 is equal to -1. Log base 2 of 1/16, we'd be asking 2 to the what gives us 1/16. Well, the correct exponent there would be -4. So log base 2 1/16 is -4. And then finally, log base 2 of 2 to the 7, we'd say, well, what exponent do we have to put on 2 to make 2 to the 7? And once we write it that way, we realize, oh, yep, the exponent's going to be 7. So log base 2 of 2 to the 7 is equal to 7. So that's the basics of what a logarithm does. Let's look at the graphs. So we're actually going to plot two functions here. We're going to plot y equal 2 to the x, and we're going to plot y equal log base 2 of x. Not necessary to have the graphs of these functions memorized, but basically we want to be comfortable enough with logarithms that we can make a table of values quickly if we need to. So let's start by plotting y equal 2 to the x. So that's an exponential function. We'll plot that one first. Let's do x values -1, 0, and 1. So as we put these different x values into the function 2 to the x, we'd have 2 to the -1, which we could call 1/2. 2 to the 0 would be 1, and then 2 to the 1 would be 2. So let's see if we can plot these points. So we've got our axes here. Let's put our x values -1, 0, and 1 on there, and then we've got our y-axis. We'll need y values up to 2. Okay, so the axes look like they're labeled in a way that will make it easy to plot these points. And let's start plotting some points. So when x is equal to -1, y is 1/2. That's this point right here. Next point is 0, 1, and then we've got 1, 2. So our exponential function, you could add a few more points to the graph if you like. Our exponential function does something like that. So it always stays above the x-axis. It grows pretty slowly on the left side of the graph and then grows very quickly on the right side of the graph. Okay, let's try plotting the logarithmic function. We'll plot y equal log base 2 of x for a few different x values. And again, this is really just practicing, helping us practice our logarithmic function, make sure we're comfortable putting some x values into this. So we could only ever put positive x values into this. We could put x equal 1/2, we could put x equal 1, we could put x equal 2, etc. So those would all be values that would be nice going into this logarithmic function. So let's plug them in and figure out what our y values look like. So plugging in x equal 1/2, we'd have log base 2 of 1/2. So we're saying, what exponent do we put on 2 to make 1/2? That would be -1. Then we want log base 2 of 1. So what exponent do we put on 2 to make 1? That's 0. And then finally, log base 2 of 2. What exponent do we put on 2 to make 2? That would be 1. Okay, so let's see if we can plot these values here. First point is x equal 1/2, y equal -1. So I'm just going to highlight where y equal -1 would be on our graph. And so this point that we're talking about would be right about there. Next point, 1, 0, and then next point, 2, 1. So our logarithmic function actually looks like this. So it never crosses the y-axis. That's because you can only put positive x values into a logarithmic function. You cannot put negative x values or 0 into a logarithmic function. And the logarithmic function grows very quickly until we get to the x value 1, and then its growth starts to slow down. So you have very rapid growth for a logarithmic function between x values 0 and 1. That's what we're seeing in our graph. So again, don't need to memorize the graph. I think the real value here was just making the table of values. So when we work with logarithms, we're going to be working with different bases, and there are two bases that are really important. The first one, base 10, and the second one, base e. So we need to talk a little bit about this number e. In words, you could call it Euler's number. In symbols, you could call it e. And your scientific calculator will have a button for e. Often there's a button like e to the x on calculators. So if you wanted to actually calculate the value of e, you would hit the e to the x button, and then you would hit 1 because you're saying I want exponent 1 on that e, and then hit equals. So something like that key sequence will allow you to find the value of e on your calculator. And if you do that, you'll find that e comes out to about 2.718. So we're going to see over the course of this video why this number e is so useful when we're working with logarithms. So for the moment, we'll just say it is an important base, and we'll see why as we go through our calculations. So some important notation that comes up with logarithms. When you write a logarithm, you always need to specify what base you're working to. So you'll write something like, log base 2 of 8 or something like that. So 2 is the base. All right, now if we just write log x like this, it looks like there's no base on there. But what that actually means is log base 10 of x. So if you write no base on your logarithm, then it's implied that your logarithm is base 10. That's why it's always important to be clear about what your base is. If you want your logarithm to be base 3, you have to say that. Because if you don't say anything, it's automatically base 10. Now, the logarithm to the base e comes up all the time throughout science and engineering. So log base e of x is something we're going to write so often that we invented a shorthand for it. So the shorthand is ln x. Okay, so I wrote this in handwriting. If you wrote it in printing, it would look like this. It's just ln x. Incidentally, the ln, it comes from the Latin for natural logarithm. So ln x, we just read it as ln x, and that means logarithm base e of x. All right, so let's do a little bit of practice with these two special bases, base 10 and base e, just to make sure we're comfortable with those. So we'll just go through maybe 4 quick points here. So part A, let's say someone asks you to find log 10. We would say, okay, there's no base on there, so that automatically means log base 10. So we're finding log base 10 of 10. In other words, what exponent do you put on 10 to make 10? The answer would have to be 1. So that makes sense. Part B here, again, there's no base on there. So it's understood that we're talking base 10. So we're saying, what exponent do we have to put on 10 to make 0.1? The exponent would have to be -1. Now we're going to do a couple of examples here, C and D, where we work log base e. So let's say someone says to you, calculate ln of e. So first thing we would do is we would say, okay, ln just means log base e. So let's rephrase this as log base e of e. And then we're asking, what exponent do we put on e to make e? Okay, the answer would be 1. So let's say someone asks you to find ln of 1 over e to the 4th. Okay, well, as an intermediate step, you could say ln is log base e. So we're trying to find log base e of 1 over e to the 4th. And then we would say, what exponent do we put on e to make 1 over e to the 4th? Well, it's going to have to be a negative exponent because that's what's going to give us the reciprocal. It would have to be -4. So that's just a quick example of working with our two most common bases, log base 10 and log base e. And remember that log base e, we usually just call it ln for short. Now calculators can only compute log base 10 and log base e. A calculator cannot compute log base 5. It would just have to have too many functions programmed into it for it to be able to compute logarithms to any base. So what we have is a handy formula called change of base formula that allows us to compute logarithms to other bases pretty easily. So this is a very handy fact when it comes to computing logarithms. We'll put a star beside that. So if you want to compute log base a of b, the formula is go ln of b divided by ln of a. So you go ln of your value divided by ln of whatever the base is. And this right side can be done on your calculator because your calculator has a ln function built into it. So let's calculate log base 2 of 5. First thing to realize is it's not going to be a nice number. So there's no whole number exponent that goes on 2 to make 5. So it's going to be some messy decimal number. And we can use our change of base formula to compute that. So according to the change of base formula, we'll go ln of our number divided by ln of our base. We can type that into our calculator, and that comes out to about 2.32. So that's how we use the change of base formula. Next thing we're going to do is practice simplifying some expressions. Again, just using our change of base formula. So for part A, what we want to simplify is log e. So we would say, okay, what's our base here? If there's no base, then it's implied that it's base 10. So we're talking log base 10 of e. And according to our change of base formula, we go ln of our number, so ln of e, divided by ln of the base. Okay, now, really important fact to remember when working with logarithms is that ln of e is equal to 1. So let's figure out exactly why that's true, and then we'll commit this fact to memory. So when we say ln of e, remember that ln is really log base e, right? So we're finding log base e of e, and we're saying, what exponent do we put on e to make e? Well, it's going to be 1. So ln of e is equal to 1, and that's going to come up all over the place. It comes up so often that it's just basically something that you want to know by heart. It's good to think through, once or twice, understand why it's true. But from then on, you just really want to say to yourself, every time you see ln e, that's 1. So that's coming up in this scenario here, because if we were trying to simplify this expression, we would say, oh, okay, that's 1 over ln 10. Ln 10, not a nice number. So this is as simplified as it's going to get. So let's try a second example like that. And now that we know that ln of e is 1, we'll be able to go through this a bit more quickly. So let's say you want to simplify log base b of e. So we'd say, okay, according to our change of base formula, that's going to be ln of e divided by ln of b. And what is ln of e? It's 1. So it's 1 over ln b would be the simplified version of that. So this little example here is going to be quite important when we jump into derivatives in a couple minutes. So we'll flash back to that a little bit later. So last thing we want to talk about in terms of our logarithm review is something called log rules. So there are 3 rules for operations that we can do with logarithms. And throughout these log rules, whenever you see base b here, that's just going to represent any base. So could be base 2, could be base e, could be base 10. The logarithm rules will apply for any base. So I'm going to erase that part just to make our rules a bit less cluttered. And let's talk about our rules. So first rule, if you have a logarithm to any base of a product, you can take that, you can split that up into a sum of logarithms. So be log to the appropriate base of your first factor plus log to the appropriate base of your second factor. So if you say this in words, log of a product becomes a sum of logs. Okay, a related rule is that if you have a logarithm of a quotient now, so inside our logarithm, we've got something divided by something, that becomes a difference of logs. So you take log of your numerator minus log of your denominator. Okay, so now we have two rules. Log of a product becomes a sum of logs, and log of a quotient becomes a difference of logs. So what if you have a logarithm of a number raised to a power? Well, that power, that n, can just come out in front. So your power n is coming out in front, and then you multiply that by log to the appropriate base of x. So you could call that the power rule for logarithms. So those are three key rules, and we're going to practice those in some examples now where we simplify some expressions. So let's simplify ln of root x. Well, first thing we would say is we can write that root x as x raised to some power. And as soon as we do that, we can use the power rule for logarithms, which says this exponent of 1/2 can come right out in front, and we can call this half of ln x. So we're using the rule that log to any base of something raised to the power, that power can come right out in front. So bring your power in front, and then you have log to whatever your base is times x. So we've used that rule there where the log base b is actually the ln function, and the power that we're working with is the power 1/2. Okay, let's do a second example of simplifying. So we are going to simplify ln of this quotient here. Let's recap our product and quotient rules for logarithms. So if you have log base b of a product, that turns into a sum of logarithms. So log base b of x plus log base b of y. If you want to make life easier, you could actually write these logarithm rules just in terms of ln, so that you don't worry so much about the base. So that would look like ln of xy is equal to ln of x plus ln of y. And then same thing for the quotient. So ln of a quotient becomes now a difference of lns. It's ln of x minus ln of y. So let's keep those rules in mind, and we'll also use the power rule that we saw above. So if you wanted to rewrite the power rule in terms of ln, just to simplify things, you could say ln of x to the n is equal to n times ln of x. And particularly for this example, just using the simpler version there might make life easier. Okay, so let's figure out how we start this. Well, inside the ln, I see a quotient. This is our numerator, and that's our denominator. So let's start with the quotient rule for ln. We'd say this expression is equal to ln of the square root times sine 2x minus ln of x plus 1 to the 4th. Okay, then in our next step, we could use the product rule for ln on that first term. So we could say that's ln of root x squared plus 6 plus ln of sine 2x, and then that's still minus ln of x plus 1 to the 4th. Now in the last step here, what we can do is use the power rule for ln. So what we might want to do is think of this square root of x squared plus 6. Let's rewrite that, squared plus 6 to the power 1/2. Okay, and that way it's a little bit more direct to use that power rule. So anytime you have a logarithm applied to something with an exponent on it, that exponent can come out in front. So we can say that's 1/2 ln of, we need brackets here, x squared plus 6, plus ln of our sine function, that can stay the same. And again, we have a power rule that we can use here because we've got a logarithm applied to something with a power on it. So we could say minus 4 ln of x plus 1. So that's how we would use the 3 logarithm rules to simplify an expression. So in this part of the video, we're going to talk about derivatives of logarithmic functions. And before we look at our derivative formulas, there's one fact that we need to know cold in order to make derivatives go smoothly. So we need to know this really well. So pop quiz, what is ln of e? Well, hopefully you know right off the top of your head that ln of e is 1, but if you're not sure about that, let's figure out how we would do this. So ln is just shorthand notation for log base e, and so we're saying what exponent should we put on e to make e, and the answer is 1. Okay, so ln of e is 1, and that's important enough that I'm going to keep that written up at the top of the screen here while we look at our formulas. So there are 2 formulas for this section. Let's start with the first one. So first formula is, what is the derivative of log base b of x? So the derivative is 1 over ln b times 1 over x. So the main part of the derivative, if you want to think of it this way, is 1 over x. And then this 1 over ln b is just a constant that adjusts that 1 over x depending on what your base is. So for example, if your base were 2, you'd say derivative of log base 2 of x would be 1 over ln 2 times 1 over x. If your base were 8, you'd say derivative of log base 8 of x is 1 over ln 8 times 1 over x, etc. Okay, now there's another way to write this. And it's really just personal preference as to whether you prefer this version or whether you prefer this version here. But if you use your change of base formula, you can say log base b of e, according to the change of base formula, is ln of e over ln of b. And we know that ln of e is 1. So that's 1 over ln b. So this 1 over ln b is exactly the same thing as log base b of e. So some textbooks will use this version, some textbooks will use that version. I'm not picky on which version you use. It's whatever seems simpler to you. To me, 1 over ln b seems nicer, but some people would argue, no, I think log base b of e looks good. Okay, so in that case, you can use that expression. So what I'm going to do as we work through our derivatives, I think I will write both versions. So our second formula is really a special case of the first formula. So our second formula tells us how to take the derivative of ln x, and the derivative is 1 over x. So let's try to understand briefly why that's a special case of what we said above. So our first formula here is valid for any base. And our second formula here is working specifically for base e, because that's what ln is. It's a logarithm base e. So if you want to figure out why this is true, I'm just going to erase this kind of reasoning that I had scribbled here, and maybe we can figure this out fresh. If we want to figure out why this is true, we'd say, okay, well, if we use the first formula, we would say derivative with respect to x of ln x is the derivative with respect to x of log base e of x, because that's what ln is. Ln is just log base e. Okay, so according to our formula above, according to this formula here, it should be 1 over ln of our base, so that's 1 over ln e, times 1 over x. But ln e is 1, right? So that term just disappears and you just get 1 over x. This second formula here is our main formula. So derivative with respect to x of ln x is 1 over x. That's beautiful. That's simple. And that's actually why working with base e is so critical in calculus, because the formulas work best when you're working with base e. We'll see that with exponential functions in our next video as well. Working with base e is where things are simplest. So that's why that number e is so important. So derivative of ln x is 1 over x. Okay, then you could say the first formula is more general. It tells us what to do if we have any other base. If we have any base other than e, there's this little adjustment factor that comes into play. So instead of our derivative being 1 over x, it's actually 1 over x times this adjustment factor, 1 over ln b. Okay, so with that, let's jump into our derivatives. We'll do a bunch of little calculations to get comfortable with these two formulas. Okay, so let's start by writing out our two formulas fresh here. So derivative with respect to x of ln x is 1 over x. Derivative with respect to x of log base b of x. It's almost the same as 1 over x. There's just this little adjustment factor, 1 over ln b, that goes out in front there. And then the other way of writing that is to write log base b of e times 1 over x, because log base b of e is just another way of saying 1 over ln b. So when I'm writing down our answers, I'll use both versions. Okay, so with that, let's jump into some calculations. The problem is going to be to find f prime of x, and we'll do a few little parts here. So part A, f of x is equal to ln x. Okay, so that's our simplest possible scenario for taking derivatives. We would say f prime of x is equal to 1 over x. Part B, let's modify that a little bit. Let's make it ln, or let's say what f of x is. Let's make it ln of 4x squared plus 1. Now we have a chain rule going on. So we know it's a chain rule because we have something more complicated than just an x in our inside function here. So let's think about our chain rule. Well, the outside function is the ln function. And the derivative of the ln function is just, you go 1 over whatever your inside function is. And then according to the chain rule, we need to multiply by the derivative of that inside function. So multiply it by 8x, because we've got something more complicated than just an x as our inside function. So our final answer would probably be written as 8x over 4x squared plus 1. So let's say our function now is log base 2 of x. So we'd say, okay, well, whenever we're differentiating logarithms, the derivative is going to be pretty much 1 over x, except there's this correction factor. It's 1 over ln of your base. So that's one way to write it, or if you prefer to call that log base 2 of e times 1 over x, that's also totally fine. Log base 2 of e, completely the same thing as 1 over ln 2. Part D, let's see how this gets a little bit more interesting if we put an inside function on there. So let's say log base 3 of 7x plus 1. So there's going to be a chain rule going on because we've got this inside function here that's more complicated than just an x. So let's write down our derivative. So we deal with the outside function first, which is the log 3. Taking the derivative of that, you go 1 over your inside function, and then because the log is to the base 3, the correction factor is 1 over ln 3. So 1 over ln 3 times 1 over 7x plus 1, all that stuff is the derivative of the outside function, and then we need to multiply by the derivative of the inside function, which is 7. Okay, so the way we might write our answer then, we might write that as a single fraction. You could say 7 over ln 3 times 7x plus 1. Or if you prefer, instead of writing 1 over ln 3, you could have written 7 log base 3 of e over 7x plus 1. So let's do a couple more parts here. Part E, f of x is log of x squared plus 2. Okay, well, first thing I would say is if there's no base on there, it's automatically base 10. So this is log base 10 of x squared plus 2. And let's think about our chain rule. So first thing we're going to do, take the derivative of the outside function, which is the log base 10 function. So we're going to have 1 over ln 10, and then we go 1 over whatever our inside function is. So at this point, we've taken the derivative of the outside function, keeping the inside function the same, and then we multiply by the derivative of the inside function, which would be 2x. So in terms of writing down your answer, you could write it like this, would most likely be combined into a single fraction, like 2x over x squared plus 2 times ln 10, for example. Or if you prefer using the log notation, instead of saying 1 over ln 10, you could have equally well called that log base 10 of e, or even log e. So you'd have log e times 2x over x squared plus 2. So those are both completely the same because log of e is exactly the same thing as 1 over ln 10. And final part here for these short derivative calculations, let's say f of x is ln of sine x squared. So you typically see brackets around it like that. So ln of sine x squared, let's try to take the derivative of that. Okay, so we'll deal with the outside function first, which is the ln function. When you take the derivative of the ln function, you're just going 1 over whatever your inside function is. Okay, and then we need to multiply by the derivative of that inside function. So I'm going to do that over 2 steps just so that you can see that chain rule really developing there. Okay, so 1 over sine x squared times, now we need the derivative of sine x squared, so derivative of the outside function, while derivative of sine is cos, so we'd have cos x squared times 2x. Okay, then if we think about how to put all this together, we've got a 2x times, we've got a cos function divided by sine of that same angle. So cos of an angle divided by sine of that same angle, that gives us cotangent of that angle. So cotangent x squared. Okay, we're using the identity here that cos theta over sine theta is equal to cotangent theta, no matter what your theta value is. So here's our next problem. F of x is equal to ln to the 4th of x cubed plus 17x plus 1, and we want to find the derivative of this. So first thing we should do is just a rewrite here. And this is an important piece of notation. So let's think back to trig functions, because this is actually where this notation comes from. If you have something like sine squared x, you can rewrite that as sine x all squared. So having a power like this on a function means that the entire function is raised to a certain power. And actually the same thing happens with ln. So if you had ln to the 4th x, what that means is calculate the value of ln x and then raise that value to the 4th power. And even if you had something more complicated in place of the x, this would still be true. So ln to the 4th of, let's say x to the 9 minus 22 or something like that, still just means calculate the value of ln of x to the 9 minus 22, and then whatever that value is, raise that to the 4th power. So this is exactly the kind of rewrite that we're going to have to do in this particular problem. Okay, so let's go back to our problem up here at the top of the screen. So we could say, oh, okay, this means calculate ln of x cubed plus 17x plus 1, and then raise that to the 4th power. So this is important because the 4th power is our outside function, and our inside function is the ln of this polynomial. So let's try the first step of our chain rule then. The 4th power is our outside function, so it's going to come down in front. The power is going to decrease to 3. The inside function will stay exactly as is. And then we need to multiply by the derivative of that inside function. So multiply by the derivative of ln of this polynomial. And I think I will break that into 2 steps, just so that there's not too much going on at once. So first part can just get recopied. And as you recopy it, what you might want to do is switch back to the quick notation. So you could say that's 4 times ln cubed of the polynomial. Because saying we've got ln of this polynomial all cubed is exactly the same thing as saying we've got ln cubed of this polynomial. And then, most importantly, let's concentrate on taking this derivative here. So we want to take the derivative of ln of this polynomial. Well, remember, taking the derivative of ln is always the easiest situation because you just go 1 over your inside function, x cubed plus 17x plus 1. There's no correction factor required when you're taking the derivative of ln. And so that's the derivative of the ln part. We've kept the inside function the same, and then we need to multiply by the derivative of the inside function. So 3x squared plus 17. Okay, and then in terms of just writing our final answer here, we would write 4 times 3x squared plus 17 times ln cubed of this polynomial. So I might just highlight things as we've used them. We've used the 4, we've used that guy, we've used the ln cubed. And so then that's all divided by the x cubed plus 17x plus 1. This is our last problem for this video. F of x is ln of this quotient, and we are going to find f prime of x. Well, this is a perfect place to use the log rules to simplify. So rather than taking a derivative of something that has a quotient, that has a power in it, and having to use, the quotient rule for derivatives and the power rule for derivatives, we could actually just use the log rules to simplify first and then take the derivative of a function that's simpler. So let's remember some of our log rules. I'm going to write this in terms of ln. So if you had ln of x to the n, that's the same thing as n times ln x. If you have ln of a quotient, like ln of a over b, for example, we can write that as ln a minus ln b. There is also the product rule for ln, but I don't think it'll come up in this problem. So just refresh the 2 rules that I think will come into play. All right, so we're working with f of x, and just going to think about rewriting that. So first thing we could say is, well, we've got a quotient inside the ln. So let's rewrite our f of x as ln of the numerator minus ln of the denominator. And then second thing we could do is we could use the power rule for ln on the first term and say that's 2 times ln of 4x plus 1, and the second term can stay the same. So I think it's important to emphasize that this is still our original function, f of x. Now that we've got that cleaned up, now we can take the derivative. So we're now saying f prime of x. I would almost just want to draw an arrow here or something so that we understand, okay, before we were simplifying our function and now we're actually going into derivative mode. So taking derivatives, okay, so this factor of 2 can just stay out in front. Taking the derivative of ln of something, your something goes into the denominator. And then if you have anything more complicated than just an x inside your logarithm, then you need to multiply by the derivative of the inside function according to the chain rule. So if you want, might be simpler just to break this up as 2 was just the constant that was out in front. We went 1 over our inside function times the derivative of our inside function. Okay, and then we go minus, same deal here, derivative of ln, you go 1 over your inside function. And then if your inside function is anything more complicated than just an x, you need to multiply by the derivative of that inside function. Okay, so technically we're done. All our derivatives have been taken, but in terms of how this would actually look, if you were checking your answer in a course pack, for example, they would say 8 over 4x minus 1 minus 5 over 5x plus 3. So that could well be how the answer is written, or they might even go so far as creating a common denominator. So you could multiply the first fraction, top and bottom, by 5x plus 3, and second fraction, top and bottom, by 4x plus 1. And then we'd have everything over this common denominator. So fast way to think about the numerator is just to think these guys have to multiply and these guys have to multiply. So that's how we get that 8 times 5x plus 3 minus 5 times 4x plus 1. And then what you would do to give your final answer then is you would keep your denominator factored. So keep it as 4x plus 1 times 5x plus 3, but we would actually expand out the numerator and then simplify. So if you expand it out, you'd have 40x plus 24 minus 20x minus 5. And then we would simplify that. And let's just make that numerator 20x plus 19. So I suspect this last version is how the course pack would typically give their answer. They usually like to give their answer in the most concise version. But of course, if you were on a test and you gave this version here or that version there, those are both correct. You've taken all your derivatives, and that's what's really important. So that was our review of logarithms. Hopefully you're feeling more comfortable with logarithms now. And then we did derivatives of logarithmic functions. Main takeaway for that is that working with the ln function is always easier than working with a logarithm to any other base. Thanks for watching.